Yes, sir. Yes, sir.
Yes, sir.
Okay, then we'll start with the basics of optimization. What is optimization? Why we want to go for optimization? What are the various parameters in optimization? The basic things we'll start with. Then we will go on to what is see what is a heuristic technique. What is the difference between a meta heuristic and heuristic techniques? Those are all the basics of optimization. Okay. Then once it is done, we'll move on to ACO analogy. Okay, the basics of ACO. What is the inspiration behind ACO? Why we are going for ACO? What's the basics of ACO? We all see these things in this talk. After that, we'll see what are the parameters in ACO. Then we'll see what are the steps. These are first four topics are the basics of optimization. Then we will go on to what is an colony optimization technique. Okay. Once you have seen ACO technique, then we will see how to formulate it mathematically, because what we are seeing till now is theoretical. Okay, just the physical explanations you will be seeing. Once you complete all these explanations, we will see mathematical formulation of ACO. Because if you want to put this algorithm into any problems, especially the power system problems we are going to see, we need to mathematically model it. So those topics we will see after this. And at the end, how to solve, if time permits, I'll tell you how to incorporate this ACO into economic discussion. Things which we are going to see today within 1.5 hours. Okay. Now let's start with what is optimization. As we know, right, most of them are using optimization technique, right? So it's just simpler. Either it is to minimize certain objective function or to maximize. Depending upon the requirement, either it will be minimizing a function or it will going to maximize a function. Okay, that is the thing, and that depends. Application. If it is a cost, we'll try to minimize the cost, generation cost. If it is a maximize the profit. Okay? So it can be either minimization or maximization depending upon the problem. Okay? And,
Sir, switch off your video.
So you don't want video also?
Okay, sir. Video is switch off so that bandwidth will be sufficient.
1 minute, let me switch off the video also. Is it okay now? Go on. Okay. So when you go for optimization technique, there are a few terminologies which you need to know. First one is objective function. That is a basic, the first thing which you'll be using in an optimization function. Optimization. So objective function means the thing which you want to optimize. Either it is a cost function, or it can be profit, or it need to reduce the losses. So which thing you want to optimize, that we'll be writing it as an objective function. The next one is decision variable. So what are the variables involved in that function? Those variables are called as decision variables. For example, we'll be working on economic load dispatch. So there the generation, there is a real power generation will be the decision variable. Or if you are using a fax device inside any problem, the parameters of this fax devices will be acting as variables. So the decision variables are the variables which are involved inside the objective function. Okay. Then constraints. So each and every function will be having certain constraints. Let me take the same load flow, one load flow example. We'll be having a lot of constraints. The thing is that if you're taking a generator, the real power generation should be within the maximum and minimum limit. Reactive power generation should be within the maximum and minimum limit. Voltage should be within these limits. So those things are called as constraints. So these are also involved in optimization. So objective function will be there, decision variable will be there, and you'll be having constraints. Okay, and the last is a termination criteria. Termination criteria means, see, it's not an infinite loop, right? So we need to end up at certain criteria. So that will be the termination criteria. It can be some condition That means whatever result we are getting, it should be less than that value, or whatever result we are getting, it should be more than that value, or number of iterations. Let the optimization run for 100 iterations, 200 iterations, like this. So finally, we need to end up with a termination criteria. So all these things will be surely there in an optimization. Inside that, you have a lot of other things, but these are the basic things inside a optimization function, optimization topic. Okay. Now let's see what is an evaluation computation. I'll just show you an example of EC. Okay. So most of the optimization techniques we are using is from nature. Nature inspired approach only. Most of the optimization techniques we are using. Either if you go for ant colony optimization, or if you are going for ABC, if you go for PSO, whatever you have, they are all inspired from nature. Okay, and you'll be having something within that you'll find the maximum. That's the process. Okay, and the basic thing which you'll be using is survival of the fittest. Who is the fittest one? They will survive. That is a basic principle. That means, as far as loss is concerned, who is giving the lesser losses? That is the actual solution. If it is profit, who is giving more profit? That will be the person who is going to survive. Okay. So I'll just tell you what are the steps involved in a basic optimization. It's nowhere related with any optimization technique. It's in general. Okay. So when you go for any optimization technique, it will start with initialization. Then you will be evaluating it. Then you will be having some condition whether to terminate it or not. Then you'll be having some selection procedure. Then you'll be having some change in the variables. So these five will be surely there in any optimization technique. Okay, I'll just show you one example for all these steps. It is just a basic example which we have. Okay, let me take initialization. Initialization means when you go for a normal analytical based technique, what generally we used to do is that we'll be having a question, we'll be having a lot of steps to solve it, and finally we will get the answer. But as far as optimization technique is concerned, it's totally different. Initially itself, we will find some answers, then we will test. That is the thing. Initially itself, will generate lot of answers. Then we will test whether this answer is best or not. What modification we can do in this. That is the condition when you go for an optimization. So initialization is just generating the initial solutions. If it is a generator, if the maximum limit is 100 and minimum limit is 10, means within 10 to 100, you will be generating one solution. That is initialization. So here I have generated 1, 2, 3, 4, 6 initial variables. Okay. See, someone is having a larger hand, someone is having smaller hands. Each one will be having one difference. Okay. So they are randomly generated. You can see 6 variables here. All are different. Okay, so initialization is a process by which you will be initializing the variables within your minimum and maximum limit. This is the first step in any optimization technique. Okay, so once you have generated this initial solution, then you will be going to evaluate the fitness function. That means you have generated some solution, whether they are fitting it or not, whether you'll be having some function, we will put these variables inside the function and we will see which are all are best. We can't tell that all the variables will give you the best answer, or we can't tell that all the variables will give you the worst answer. Okay, so there are some variables which will give the best answer, there are some variables which will give the worst answer. So first of all, after generating these variables, we need to evaluate the fitness. What is the answer they are giving? Which one is giving best answer? So in this example, I just took this hurdle as an example. That means the solution, the person is here in this picture. You can see 6 people are there. They need to jump this hurdle. Okay, that is actually the condition. So how long they are going? That is the best. Okay, how long they can travel in this? That is actually the best one. That is the condition which I have given. Okay, so let me take the person A. Actually, his height is very less. So he can go only up to certain distance. You can see he can go only up to this range. Beyond that, he can't go. So his fitness value is taken as 250 from this one. Okay, his fitness value is taken as 250 from this one. Okay. Yeah. So this has to be tested for all the solutions. If you're having 100 solution means for each and every solution, you need to test the fitness value. Okay. Now I'm testing for the second person. Actually, he's actually you can see the third person. So he can go up to certain limit. Up to 350 he can go. He can jump up to 350. So the fitness value for him is 350. Okay, so from 250, the second one is having 350 value, and you can see the third person is very small. Okay, he can reach only up to this some 240 or something. That's all. He can't go beyond this level. So his value is 240. So like this, for each and every solution which you have generated, you need to find the fitness function. Okay, that's what. That depends upon the fitness function. Depends upon your objective function. That is depends upon your problem. If you want to minimize the cost means each and every variable we will put it in that equation and see what is the cost. If you want to minimize the losses means whichever variable you are generated, we will put that variables inside the expression and we will see what is the losses. That is actually what we are going to do. So I've shown this for three variables. Okay, I'll take this for another three also. It's like this. These are all examples. Okay, so the first variable has a fitness of 250, can reach up to 250. The second person can go up to 350. The third person can go up to 240 like this. That's the condition. Okay, this is actually the evaluating the fitness. Okay, now we are evaluating the fitness. Then we need to see whether the termination criteria is achieved. See, termination criteria can be anything. Okay, you can tell that my value, whatever value I am getting, it should be less than e power minus 6. Okay, or whatever value I am getting, it should be maximum. Or you can tell that it has run for whatever value you are getting, it has run for 100 iterations. So any termination criteria can be fixed. If it is meeting any of this criteria, then that will be stopping, and the person who is having the best value will be the actual solution. Okay, but assuming that this termination criteria is not met. Okay, so what we need to do is that out of 6 people, who are all the best, we need to take. You can see the first person is having 250, second is having 350, and here 320. So what the thing is that these 3 people are having the best compared to others. Okay, so you'll be having certain limit within that only you can take. You can't take all the 6, or you can take only the 1. So depending upon the probability, you'll be selecting who are the best. Okay, so in this one you can see the person A, he is having 250, the person B is having 350, and the person D is having 320. So all these people they are best. Okay, so they are taken. That is actually selection. Who are all the best? Depending upon the fitness function, who are all the best? Okay. See, this is actually a maximization function. That is why we're all having maximum value. They are taken into account. Okay. So now these 3 people are taken out. Okay. So they gave best value compared to the remaining 3 people. Now the next one is that, see, as far as optimization is concerned, it's not a single one. Right? Once you get a best solution, what they'll be doing is that they'll take the variable, they'll do some modifications. Okay, they'll do some modification, and with the newly created variable, they will test whether they can get better result compared to the previous case or not. That's what they'll do. I got 3 variables now. Each and every variable has some certain properties. One person can easily jump, one person can easily run. So each and every one are having their own properties. Okay, so with this one, they'll be creating new different variables like this. Okay, see, they have created one more variable. This gray color is from this first person, third person, and this color is from this second person. Okay, so they mixed the property of these 2 persons and they have created a new variable, because each and every variable has some advantages. Okay, so when mixing all these things and creating a new variable, we can expect that the advantages of all these variables will be added up. That is the assumption. So now a new variable is created as D, which has a property of B and C. Likewise, we'll be creating another 3 variables with their properties. Okay, so 3 variables we are created. They have the property of all the C. The first one is having the property of B and C. The second one is having the property of A and C. Third one is having the property of A and B. Like this, we will be creating 3 more. Now the thing is that these 3 variables will be checked again for the fitness function. Okay, so the total now we have 6 variables, right? So these 3 newly generated variables will be checked for the fitness function. It's like this. First generation has these many people. Second generation, from this first generation, 3 people came into second generation, and the 3 were newly created. Now we have 6 new variables. So with these 6 new variables, again they will check the fitness function. In that also 3 will be best, 3 best will be taken. So they'll be going on changing like this until the termination criteria is reached. This is actually the basics of any optimization algorithm. And only the steps which is followed will change, because initialization is same. I mean, initialization step is there in all algorithms. termination is there, fitness function checking is there, in all algorithms it's there. Only the middle part will change. If I go for ant colony, the behavior of ant will come in the middle. If I'm going for ABC, the behavior of honeybee will come in the middle. So that depends upon the algorithm which we are using. This is the basics of any optimization function. Okay. Now let's move on to what is a heuristic optimization, because normally we used to hear this heuristic optimization, meta-heuristic optimization, like this it will be there, right? ACO will come under meta-heuristic. So if we go for a heuristic optimization function means, okay, it's actually problem specific. Okay, for each and every problem they have certain rules and regulations, so it's problem specific. That heuristic methods means it's problem specific. And a very important thing is that the knowledge about the problem you need to know before you are applying this heuristic algorithm. Okay, so heuristic algorithm means it's problem specific. Okay, and if you want to know, if you want to solve such things, then you need to know about the problem, then only you can solve it. Whereas meta-heuristic is problem independent. Only algorithm will be there. You can put any problem in. They are problem independent. That means algorithm is fixed for all problems. Yeah, we don't want to change anything depending upon your problem. Algorithm is fixed. It's independent of the problem. Okay, and we don't want to know anything about the problem. Okay, without that we can put it into picture. That is the difference between heuristic algorithm and meta-heuristic algorithm. Okay, but the thing here is that, okay, we can't expect that always we'll get the optimal result. Sometimes you can get a better result and sometimes you can get a worse result. Whereas when you go for some analytical methods, you can get best results. That is understood. Okay. The thing is that, for example, if I'm having I'll just tell one example. What's the difference between normal analytical algorithms and this optimization algorithm? Is that consider that I have a computer. Consider that I have a computer. Okay. Some issues have been, some issues came with that and it got shut down. Okay. So if I'm using an optimization technique, the solution it will give within 10 seconds that restart. That's it. Okay. That means the solution which you're getting is very faster. Okay. Within short time, you'll get the solution and it will tell to restart it. But the thing is that either restarting may solve your problem or may not solve your problem. That is different. That means optimization techniques are very fast, but you can't expect that the result will be best always. Sometimes it will be best, sometimes it can go worst. Whereas when you go for analytical techniques, same computer if it is shut down, what solution it will tell is that we need to take the manual, we need to see all the instructions inside that, for what problem, for repairing we need to see inside, then repair all these things, then use the computer. That is actually the solution which will be given by an analytical. Here it is time consuming, lot of rules and regulations will be there, rules and things will be there, it's time consuming, but the thing is that you will get a perfect answer at the end. That is actually the difference between a analytical method and this optimization. Okay, that is why when you're using optimization technique, once you're running, you'll get some better result. But the next time when you're running, surely you won't get it. Okay, the result, because all optimization algorithms are random. Only will be generating things in random and we'll be using it. Okay, so you can't expect better result always. Okay, so this is the difference between heuristics and meta-heuristic algorithm. Now, let's go to SWAM. Okay, that's what we have. SWAM means actually it's a group of people, I mean group of things. Okay, all these algorithms will come under SWAM only. Okay, if I'm taking a PSO, it's a group of birds. If I'm taking ABC, it's a group of bees. If I'm taking ACO, it's a group of ants. If I'm taking CSO, cuckoo search algorithm, it's a group of cuckoo birds. Okay, so SWAM intelligence means it's a group of things. Okay, it's a group of that depends upon the algorithm what we have taken. Okay, so what decision they are taken inside the group, the same thing is replicated inside the optimization technique. So SWAM intelligence means a group of things will be there, their behavior will be considered as an optimization algorithm and it is used. That is actually SWAM intelligence. Okay, now let's go on to optimization. What is anchor? These are just an introduction. What is an optimization technique? What are the parameters in optimization? All such, they are basic. Now let's go on to what is ant colony optimization. Okay, so this is first proposed by Dorigo in 1992. Actually, it was his PhD thesis. First proposed in 1992. Even nowadays, it's used for most of the applications. It's used for most applications. The first version was called as AND systems. When it was proposed in 1992, the first thing was called as AND systems. Okay, but we have a lot of improved versions. So initially it was AND systems. Now we are using it as AND colony optimized ACO. We have a lot of improvement with the initial one, and we are using it as AND colony optimization. And now a lot of other versions are also there. Turing and colony optimization, nodal and colony optimization. So a lot of other certain things are there. But the basic one which you are using is and colony optimization. That is ACO. Okay. It's actually heuristic. It's actually meta heuristic. It's a population based algorithm. That means a population of ants will be there. Their behavior is converted into an algorithm. Okay. So it's a population based algorithm. It's a probabilistic. We have a lot of probabilities inside. And the last one is meta-heuristic. So it's proposed in 1992 by Dorigo. Initially, it is called as an AND system. Now it is called as AND colony optimization. It's a meta-heuristic technique. That means you have specific algorithm there. You can use it for any of your problems. It won't change with respect to the problems. Okay, steps will be the same for all problems. Okay, so that is meta-heuristic. Okay. I'll just take one analogy. This from this I'll tell you how the ant colony has reached ant colony optimization came. This is a basic analogy which will help you to understand what is happening inside ACO and how that came. Okay, so this is actually a big story behind this one. You have a source that is actually a village, and you have a destination. Okay, let me take this. Um, okay. You have a source, it's a village, and this is a destination. You have some pond or lake somewhere, you need to take water. Okay, so this happened very, very long back. At that time, you don't have any vehicle or you don't have any GPS or anything. The people in this village, they'll be daily going to take water from the pond and they'll be returning. And they have two paths, okay, but they don't know which path is the shortest. Okay, they don't know which is the shortest path. At that time, you don't have any vehicle or any no GPS system, nothing is there to find which is the shortest path. So daily, some people used to go to the first green path and someone will be using the second red path. Okay, so one day what happened is that two people, that is person P1, is actually an analogy. Person P1 and P2 try to find out which is the shortest path. Okay, so what they have decided is that they will be taking each path. Person one will take path one, and person two will take path two. They'll be going and taking water, and while returning, they'll be pouring water in the path. That is the condition. They'll be while returning, they'll pour water in the path. Okay, so if depending upon the wetness of the path, then they can identify which is the shortest path. That is actually, this is a very important concept because there is no communication between two people, person and person two. They are not communicating with each other. They're simply seeing the wetness of the path and they are identifying which is the shortest path. This is a very important term in ASO. This is generally called as stigmergy. I'll explain what is stigmergy later. There won't be any communication between these people. Initially, they'll tell that you just go take water, pure water in the path and come, and depending upon that, we'll identify which is the shortest one. So person one, what he did is he just started from here, okay, and he went this path. But you know, person path two is very lengthy. So when person one has reached the destination, person two came up to this place. Okay, this is a normal one. Okay, now the person one, he has taken water and he is returning back. Okay, clear. But at this time, what happened? Person one has reached here. Okay, he is taking water, and when he is returning back to this one, see, as per the condition, when they are returning, they need to pour water in the path. Depending upon that only they can understand. So when the person two comes to this place, he can see this path is wet. Okay, this path is wet. So he can understand that person one already came to pond, he took water and he left that place. So it indirectly tells that path one is the shortest path. Okay, because you have wetness in the path. So what happened is that person two also took the same second path because path one, path two, there is no wetness. Path one already person one has returned, so the path is wet. So depending upon that, he has understood that the path is wet. That is the shortest path. This is actually the analogy. The same analogy will be used in and colony optimization. Okay. Let me go to the next slide. Okay. Now let's take a condition. Okay, because it's an optimization technique and they are human beings. We can't predict anything, right? Let me consider one more condition. The person one has reached this one path. He took water and he has returned. That is a usual thing. But person two, he initially went up to this, and as per the condition, he has to take the path which is wet, but by mistake, again he has taken this second path. This can happen, right? By mistake, he can take the second path without seeing the wetness in the path. Again, what will happen? This person will reach is source, okay, but this path 2 is very large, so within person 2 reaching the source, person 1 has person 1 would have been went twice again, like this he would have returned again. That means before person 1 is completing this, person 2 is completing one round, person 2 has completed two rounds. So person 2 by mistake he has taken his old path and he has came to his source. But while going for the second time, he can understand that this one happened twice. This person has came in path one. So path one is much better compared to path two. So again, if there is some mistake also, now he can realize that path one is the shortest path. So this is the basic analogy behind the ant colony optimization. Okay. Right. Now let's move on to ant colony optimization. Okay. So behavior of ants. Okay, ants will be going to search food from their nest. The behavior of ant is utilized as an optimization technique in this. That is actually the way. Okay. And here we have two important things. Okay, two important things when you go for ACO. The first one is stigmergy. Stigmergy means, okay, without direct communication, they'll be understanding things. See, in the first analogy, we have seen that there is no direct communication between person one and person two. But by seeing the wetness of the path, person two has understood that path one is the shortest. But that wetness came because person one has poured water in the path one. So person one is doing something and person two is following that. Okay. But there is no direct communication between the first and second person. That is called as stigmergy. Okay. Stigmergy is an indirect communication between people, interaction with some environment. Okay. That means one person will do something and second one will respond for that. But there is no direct communication between the first person and the second person. This is called as stigmergy, and this is employed. This mostly you can find it in ant colony itself, and that is employed in ant colony optimization. And the second one is, see, in the first analogy, we have seen water. Okay. So water, that is the wetness of the water is there. The same thing when you come to ant colony, you have something called as pheromone. Okay. Pheromone is the thing which is used in ant colony. Because when the ants are moving from one place to another, they'll secrete something called as pheromone. Through that only ants will be communicating. So most of the things you can find that ants are blind. Okay. So this is the only way and can communicate between each other. So they'll be laying pheromones. Okay. Okay. So species lay pheromone trails traveling from nest. So wherever they are going, they lay something called as a chemical called as pheromones. So in the first analogy was in water, same as that here when you are going, when ants are going, they lay something called as pheromones. Okay. And one more important thing, pheromones can evaporate. You have seen water, they'll pour water in the path and they'll come. But after some time it can evaporate. Same as that the pheromone which are laid by this ant can evaporate. That is important. Okay. And when a same path is used by multiple number of ants, then the pheromone content will increase. One ant will secrete pheromone and it will go again. Second ant will is going through that path, it will again secrete pheromones and it will go. So as it is traveling from one, as more number of ants will be traveling in a path, the pheromone content will increase. So this is pheromone. So two things, one is stigmergy, another one is pheromone. Those two are important ant colony. Hello? 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 So any
Hello.
issues are audible?
No, sir, audible, sir.
Hello.
Sir, audible, sir.
Good. Most of the hands are blind. Okay. And whenever the hand is moving, they'll play something called pheromone. Okay. And pheromones will be deposited in the path, and depending upon the pheromone content only, the hands will move. In a place where if they are finding more pheromone content, the hand will keep like this. If there is a less pheromone content, they'll go to the path where we have more pheromone content. Okay. So pheromone, more pheromone in the path increases the probability of path. Less pheromone content means and you will search for another path which is having more pheromone content. This is the basic thing. Through this only, the entire optimization technique is working. Okay, now let's see an example here. Okay, how yes, this is actually a basic structure of PCO. How ant colony optimization is working. Okay, so I have a nest here. Okay, and I have two ants. See, in an ant colony, you have n number of ants. Just for example, I'm taking two ants. Okay, one is red in color, other one is purple in color, and they are going from the nest to foot. Okay, so this is actually the entire explanation of ant colony welcoming. Okay, now, so these ants, two ants should go for search of food. They need to take food and they have to come back to the nest. That is the condition. So first ant, red ant, it is moving here, okay, and the purple ant will also move up to this. So, but the thing is that this is the initial case. So there is no pheromone content in any of the paths. Okay, so the ants can either take upper path or they can take lower path. It is optional. So since you have only two paths, so you have 50 percentage, okay, probability for the upper path and you have 50 percentage probability for your lower path because there is no pheromone content in two paths. So either they can take the upper path or they can take the lower. Okay. So assuming that and one is taking the upper path and it is reaching the nest. And whereas and two also assuming that it is taking the lower path and it is reaching the foot. And after taking food, they'll come back. And again, after taking food, this ant will also come back. Again, next probability, because you can see in the upper path you have only one line, and in the lower path also you have only one line. So the pheromone, since the distance is the same, the pheromone content in the upper part and in the lower part will be the same. So since only 50% chance is there, the ant can take any path. Either it can take the upper path or it can take the lower. So considering that these ants are taking same as the previous one, he is taking the upper path and he is returning. Whereas since the probability is the same from both sides, this is taking the lower path and they are returning. Still, there is no optimization here. Okay, because all paths are the same. Now let's see, let's go to the third time. This ant is coming here. Okay, and blue is coming here. Again, the same probability. If you see the upper part, you have only two lines. Lower part also you have two lines. Okay. So this since probability is the same, this person, this red ant, it's taking the upper path and is going to the nest. So since same probability is there, assuming that this blue ant is also taking the upper path and it is going to the nest. Okay. So now both the ants, since probability is same, 50-50 is there, both are taking the upper path and they are going. Now what will happen? While returning, you can see, hello? While returning, you can see in the top you have four lines. In the bottom you have only two lines. Okay, that means the pheromone content in the upper path will be more, and the pheromone content in the lower path will be less. So now what will happen? The probability will change because upper path is having four and the lower path is having only two lines. So now the this proportional will change. So these 4 are there, these 2 are there. So surely this probability will be upper path will have 75 percentage probability and lower path will have 25 percentage probability. So surely the probability is more in the upper path. So surely both the answers will be in the upper path. So finally they will make that as a shortest path. And one more thing, what happens is that whenever the ants are secreting pheromone, it will evaporate with respect to time because it won't be there same as always. It will evaporate with respect to the time. So considering that this line came at the very first time and this line came at the very first time, they are evaporated. So this line got evaporated and this line got evaporated. Now also you can see in the top you have 3 lines and in the bottom you have only 1 line. So the percentage is around 70-30. Yeah. So surely the ants will take the upper part. This is how they are finding the path. But in this example, there is no shortest path because both the paths are the same distance. Okay. Even though both the paths are having same distance, initially they'll go through different paths, but finally they'll take only the one path. Okay. Since the both are of same distance, there is no shortest path in this case. Both are the same, but they are taking one. Okay. So now let's see if these two paths are different, what will happen? This is actually happening in ant colony optimization technique. So assuming that both the paths are different. Okay. So first path in the top is having the distance is more, and the second path is having less distance. This is straight. Now let's see how ant colony is working. Second. Okay. Now let's see. This is a purple ant. Okay. Initially, this ant will come up to this, and this red ant will come up to this. Okay. And see here, it's an initial case. There is no probability of upper and lower path because there is no pheromone content in the upper and lower path. So they don't know which is the shortest path. There is no pheromone content in the path. So surely the option there is 50 for up and 50 for lower path. Okay. So the probability is just 50-50 only. Okay, because there is no pheromone content, they can take any path. So assuming that this person is taking the upper path and he is going to the nest. And this person is taking the lower path and is going to the nest. But assume that, okay, consider that, okay, this person, both of them are starting here and both of them are reaching here. But you know, this path is very small. So what will happen when this person is reaching this path? This person would have reached only up to this. That's all. Okay. So because if you see the distance, this path this is smaller and this is longer. So after this one, what will happen is that since he has taken foot, he will return in this one. So now you can see one path. Now this person has already reached this one. One is there, and he will check it here. Now we can see this person will come here and he will check the probability because in the top we have only one line, whereas in the bottom you have 2 lines. So the pheromone content will be more in the second path compared to the pheromone content level in the first top path. Since the pheromone content level is very higher in these two paths, so this ant will take the same second path because the pheromone content is more here and this is less here. So now see the probability, the top is just 30 and the bottom is 70. Okay. So the shortest path will have more pheromone content, whereas the longest path will be having less pheromone content. So always depending upon the pheromone content only, they will take the path, and it is understood that surely it will take the shortest path. This is actually what is happening in ant colony optimization. You can see when you are seeing, and also if you have a source and if you have a destination, if you have a food source somewhere, initially ants will move randomly. Some ants will go in one direction, other ants will go in different direction. But after some time, you can see they'll be having only one line. There you can see practically, right? Initially, they'll be going here and there to reach the destination. I mean, to reach the food source. But after some time, you can see only one line will be there. All ants will be following the same path. That is because of this concept. And the same concept is used inside the problem. That means inside the optimization technique. Hope up to this it's clear. Okay, so first analogy is for the basics of optimization for ant colony, and this one explains you how ant colony optimization is working. Yeah. Okay. So now actually I have a shortage of time. I need to wind up within 5:30. What I'll do is that whatever explanations I have given here, that is explained here. What is ant colony optimization? Okay, how the steps are followed. I just gave us here. Okay. So since you have shortage of time, not taking all the theories. I'll just give a glance what is inside. Okay. So when you go for ant colony optimization, ants will move from source to the nest to the food source. Okay. And initially they will take any path, but after that they'll take only one single shortest path. Okay. The same concept is used as an optimization function. Okay. So they runs more or less randomly. Once they are finding a source, it returns directly. So the thing is that so ants, what they will do is that while returning, they'll see the path which is having more pheromone content. They will take only that path. So when more number of ants are traveling in that path, the pheromone content will going on increasing. And after some time, you can see only one path will have more pheromone content, and all the ants will be following through that path only. And surely that will be the shortest. Okay. So that is the concept behind ant colony optimization. Okay. Yeah, returning to the useful strength and these are the basic things what I have told till now. Okay, so this is actually this is a diagram you can see. This is actually good. Okay, so and in this diagram you have two different parts. Okay, in this diagram you can see two different paths are there. One is this path and one is this path. So initially ants can take any path, okay, but after some time you can see they'll take only one path which is the shortest. That is actually the property of ants. It's the quality of ants. The same thing is used as an optimization. And this is the thing which I have explained till now. Okay, the same thing that I have explained. Okay. So keep in mind, one is stigmergy, another one is pheromone. Stigmergy means there is no contact between the first and second, and they are not talking to each other. They will never tell that I came to the shortest path, you came to this. There is no communication between them. Depending upon the pheromone content only, they will understand. So stigmergy and pheromone, these two are important concepts when you go for ant colony optimization. Okay, you can see here. So even though if you have two different paths, finally all the ants will take the same shortest path. That you can see practically also. Okay. See, I'm not going much into theory like this. As I explain the concept, the same because of shortage of time, I explain just the basic concept of ant colony. Okay. Now, see, you have seen ants will travel from here to there. They'll go in search of food. So they'll raise pheromone contents. Pheromone will evaporate. All such things are there physically. Okay. But when you're putting inside any problem, okay, we can't tell all these things, right? We need to convert these things into equations if you want to put all these things inside a optimization technique. Okay. That means, for example, I'm telling that ants will go from one path to another path. So we need to write equation for that, how it is going. What is the probability? Ants will secrete pheromone. So what is the expression for pheromone? How to mathematically write the expression for pheromone? Then pheromones will evaporate. Okay. So what is the probability of evaporating? Whether all the pheromones will be evaporating or it will stay like that. Okay. So what is the condition for that evaporation? So that will also has to be converted into some equations. So what then? Once depending upon the more pheromone content, ants will choose the same path. So at what probability they are choosing the same path? How they are choosing the same path? All these things has to be converted into mathematical equations if you want to put all those inside the problem. So now I'll tell you how to write. It's simply 4 or 5 equations. That's all. How to write all these concept of ant colony as mathematical model. Okay, because when you're going to solve any problems, you need to write programs. Programs need these code, these equations only. Because pheromone you can tell simply, but what is pheromone? What is the expression for pheromone? That we need mathematically. Then only we can put all these inside the optimization function. Okay. So just a recap, is it audible till now, sir? Hello? Hello?
Yes, sir.
Audible
Sir,
now, right?
audible. Yes, sir.
Okay, because I'm not sure network is there or not. I'm continuously presenting, so just that I'm asking is there. Okay, let me go for the next one.
All are there in Unicode, sir.
Okay, sir. Okay, because since it is very silent, I don't know whether I am disconnected from the network or not.
No.
We involved a lot, sir.
Okay. So now let's see how to, just within 30 minutes, I'll tell you how to write expression for these and colony optimization with one example. It's very simple example. It's very easy to understand. Okay. Now, see, when you go for ant colony, we have only two important things. One is pheromone. Okay. How to model the pheromone? Okay. Because they are secreting pheromone. Depending upon that, only the entire process of ant colony is taking place. So, how to model pheromone? How to find how much evaporation is there? That is very important. Then, second one is decision making. That means depending upon the pheromone, how they are following the path. Those two are very important. These two only we are going to convert it into equations. Okay, so let's start with the first one. With one example, I'll tell you. Okay, so in this example, okay, see, I have four places. 1, 2, 3, and 4. I have 4 nodes. Okay, so these numbers will tell you what is the distance. That means distance between these is 1. There can be kilometers, whatever it may be. The distance between these and this is 4. The distance between these and this is 5. The distance between these and this is 15. It is 8. Like this, these numbers will tell you what is the distance. Okay, so the condition is that, okay, if I am taking an ant, it has to start from here. Okay, it has to start from here and it has to go to the destination and it has to reach back. So it has to start from here, it has to go to the destination, this D, and it has to reach. But it 1, 2, 3, 4, all such paths are there. It can take any path. That is the condition. Okay, either it can go like this and it can come back. Okay, or it can take this path, then it can go zigzag, then it can reach the destination, then it can go like this, then it can come back. So it can take any path. The only condition is that it has to start from the first source, it has to reach the destination, again it has to return back. That is a condition. Okay, so again, this is the next one is pheromone. These are all just example I have taken. And the pheromone content in this path is taken as 1. The pheromone content in this path is taken as 3. This is assumed to be 4. These are all just assumption only. Okay, it's just assumed. Okay, so the pheromone content in this path is just 1. The pheromone content in this path is 10. Like this, it is assumed. Okay, so my thing is that I have an ant. It has to start from one place. It has to reach the destination. It has to come back, and it has to go only through the shortest path. Okay, now let's see how to model this one. So pheromone content is given by this expression delta tau. The delta tau means it's a pheromone content. Tau is for pheromone content. Delta will take it for one and delta tau. Okay, I'll just take annotation here. Delta tau is the pheromone content. K is for ant number K. Okay. See, if I have 10 ants, it can K will be 1 or K can be 2 or K can be 3, anything. Okay. So K is for ant. It is a kth ant. Okay. J means it is I is one starting end and J is the finishing end. Okay. See, if I am taking one path here, it will have a starting and it will have a destination. So this is taken as I and this is taken as J. Okay. So one ant is moving from I to J. That is the thing. This is I and this is J, a K, and it's moving from here to here. So delta tau is the pheromone content. The ant is separating. K is for the kth ant. Ij is for the path. So it is given by 1 by Lk. L means the distance. The distance is L. That is the case. So why it is 1 by Lk means actually we need to find the shortest path. Okay. So as per the condition, the pheromones once it is secreted, the shortest path will have the more pheromone. Whereas longest path should have the less pheromone content. That is the condition we want. Because we need to go with the shortest path. That is what we want. So shortest path should have more pheromone content and longest path should have less pheromone content. That is why it is taken 1 by distance. Okay. So if the distance is more, pheromone content will be less. If the distance is less, pheromone content will be more. That is the condition is. Okay. If it is for going through the longest path, the pheromone content will be less. If it is going to the shortest path, the pheromone content will be more. That is why it is 1 by LK. 0 otherwise means if it is not following this IJ path, then it is 0. If it is going through IJ path, this is a value. And if it is not going through IJ path, it is 0. That is the basic thing for pheromone. Now, but the thing is that one path is there, it doesn't mean that only one ant can go through that path. Any number of ant can follow that path. So the total pheromone content in a path will be the sum of the pheromone secreted by all the ants which is going to the path. Clear? If I'm taking path ij, it doesn't mean that only one ant will go through the path, that k ant. And number A can flow and B can go, any number of ant can flow. So at any particular time, the total pheromone content in the path is the sum of pheromone contents secreted by all the ants. Okay, so you will be having expression like this. Okay, so here there is no delta because it's a total pheromone content. So total pheromone content is given by tau. Okay, yeah. So its k is equal to 1 to m. Okay, so which is tau which is available in Ig. Okay, so this k you leave it, it came by mistake. Okay, so it's tau Ij is tau means the total pheromone content in Ij path is the summation of k equal to 1 to m. 1 to m means total m number of ants are there. So each and every ants they will secrete pheromone that will be added up. See this k is not there. Okay, yeah. So this is actually the total pheromone content in the path. Summation of the pheromone content by all the ants. Now let's see the example which you have seen. How much pheromone content is there in the path? Okay. Okay. Now I'm assuming that see I have two ants. Okay, they can take any path. So the condition is that it has to start from the source, it has to reach this destination, and it has to come back to the source. Okay, you can see I have a blue color ant and I have a green color ant. See, blue color ant it has traveled in this path. Okay, assuming that it has traveled in this path. You can see green color ant. It started from here, it's gone here, it went up to this, it came back like this. So they can take any path. Just for example, this path is given. Okay, so let's see. We know that the expression for this pheromone is 1 by LK distance. So let me take the blue ant. It is starting in this path. It's 4. 4 plus 5, 9. 9 plus 4, 13. Plus 1, 14. That means this ant has traveled 14. And the total pheromone content is 1 by 14. Okay. Yeah. And if I am taking green ant, it started from here. So this path is there for green ant, it is 4. This path is there for green ant, plus 4, 12. It is 12 plus 4, 16. And it has 15, so 31. So the green ant has traveled 31. Hope you can understand from this expression, I mean this diagram, right? Blue ant has taken 4 plus 5, 9. 9 plus 4, 13. Plus 1, 14. Whereas green ant has taken 31. So the total pheromone content in this is 1 by 31. Okay. So this is how we will be calculating the pheromone content. It is depending on the distance. Longer distance means less pheromone content. Shortest distance means more pheromone content because we need to find the shortest path. Now, let's see what is the value for this. So this is for only one ant. Okay. Because I just took it separately for the ants. This is for the first ant and this is for the second ant. But you can see this path, 2 ants have gone. This path also 2 ants have traveled. Okay, so we have seen one summation, right? Total pheromone content is the sum of the pheromone content in that path. So this path is only one ant is going, that to the green ant. So it's 1 by 40. Okay, so this path you can see blue and green and they are going, so it's 1 by 14 plus 1 by 35. And this path only one, and this path both ends are going. So this is how we will be calculating the pheromone content. Okay, so in certain path only one ant will go, in certain path both the ants will be going, and finally you will get an answer like this. Okay, I think this is the answer. Yeah, this is how with that equation you'll be calculating the pheromone content. So this ferromene content in this path is 0.07, it's 0.1, it's 0.03, it's 0.03, it's 0.07, and this is 0.1. Okay. See, from this itself we can understand which is the shortest path, because this is 0.1. So surely this is one shortest path. This is 0.1, it shall be a shortest path. Okay, but still, just I want to explain this. So this is how the first one is done. How you will be calculating the ferromene content in an ant colony optimization. First, calculate it individually. Okay, then see how these ants are going in the path, then add it accordingly. So finally, you will get a ferromene content like this. So this is how you'll be calculating the ferromene content in each and every path. But one more thing is there. See, this ferromene content is not fixed. It will evaporate with respect to time. Okay, it will evaporate with respect to time. Okay, so this is not a fixed value. This is just a calculation. So, but pheromones will evaporate. So that is the next expression we want. So first expression we wrote it for pheromone content. Then we wrote it for how to calculate the total pheromone content. And next expression is how to incorporate the evaporation. So this is how you are incorporating the evaporation. This is actually the ferromene content. As of now, you have this K won't be coming. Okay, so this is the ferromene content which the ant is going to give, and this is the ferromene content which was already existing. So, for example, at a particular point of time, what is the ferromene content means? What it is there now plus the previous one. Okay, and there they are incorporating this evaporation factor. Evaporation factor is given as rho. Okay, because pheromones will evaporate. Okay, so for example, assume that in the first case it was 5 and the second case it is 10, it will be 15. That is a normal thing. But what will happen is that first case it was 10 and it will evaporate after some time. Okay, so for this 5 we need to add the evaporation factor. Initial case, this 10, this is a new one, so it will stay as it is. Yeah. So this rho as evaporation will range from 0 to 1. If you are putting the evaporation factor as 0, it understands that there is no evaporation because it's 1 minus 0. So the previous one surely will get added. So then you will get 15. If you make the evaporation factor as 0. But practically that won't happen. Some evaporation will be there. So if you are taking the evaporation factor as 1, then nothing will be left for the previous case. Whatever you have at present only will be there. Okay, so evaporation factor varies from 0 to 1, but you can never take 0 or 1. 0 indicates that there is no evaporation, 1 indicates that everything has evaporated. Okay, so normally you will be taking a value between 0 and 1 for the evaporation factor. This is the third expression for evaporation, incorporating the evaporation factor. Let's see, when you are incorporating this evaporation factor, how this pheromone is changing. Okay, so this is the first one without ferromene content. So this is the expression without evaporation factor, and this is the expression with evaporation factor. And I'm assuming that, see, for finding the evaporation and all, we need something what is previously there. I'm assuming that previously I had everything as 111. Just for simplicity, I'm assuming that the previous case I had all 111 as ferromene. Now let's see if I'm putting evaporation factor inside that, how the pheromone will change. So considering that the evaporation factor was 0.5. That means assuming that 50% has evaporated. So this is the equation without evaporation. You can see it's 1 by 14 plus 1 by 31, which you already seen. But this expression is with evaporation factor, and you can see this one is here and this one is here. Okay, assuming that the evaporation factor is 0.5 and initially the tau value was 1, this is the difference in calculation. So this is the first one with total pheromone content, it's going like this. And if you are incorporating any evaporation factor, your calculation will change like this. Okay, so finally what you will get is, you will get like this. You can see if you are incorporating evaporation factor, initially it was 0.1, now it is 0.6 with the previous case. Okay, so you have incorporated evaporation factor. Since the evaporation factor is incorporated, all these answers will change. Okay, if it is not incorporated, this will be 1 plus 0.1. This will be 1 plus 0.007. It will come like this, but you have incorporated the evaporation factor. So everything will be coming like this. So when you're going for ant colony optimization, first you need to write the expression for pheromone content, that is tau expression. Then you need to sum all those things so that you'll get the total pheromone content. And finally, you need to incorporate the evaporation factor. This is the third expression. So totally, you have only 3 or 4 expressions in ant colony optimization. Okay, this is how you want to calculate the pheromone content in any path. So this step is done. Hope it's clear after this. And let's move on to the last one, calculation of probabilities. So, okay, still I have all these pheromone contents, right? I have all these pheromone contents. But the thing is that if I am taking an ant from here, it can take this path or it can take this path, it can take this path also. So what is the probability? What is the probability of taking this path? What is the probability of taking this path? And what is the probability of taking this path? That we need to tell because it's an algorithm, right? So if we need to give some expressions to select the paths, because if I am taking ant, they can understand the pheromone content and they can go to the respective path. But when you go for a technique, we need to write expressions for that. If the pheromone content is this one, you take this path. If the pheromone content is this one, you need to take this path. So now we need to find what is the probability. You have only 3 paths. One is this path, other one is this path, and other one is this path. And ant can take any 3 and after 3 paths. So depending upon this pheromone content, what is the possibility to take this path? That is the next one. So if you can do that expression, then most of the things in ACO will get. That's all. Okay, so this probability of taking a path is given. This is standard equation. It's given by this P will indicate probability. Ij means probability of this is the pheromone content. Okay, and this eta is with respect to the distance. This is the expression for calculating the probability of the path. And this alpha is a factor and this beta is a factor. I'll tell you what are these factors and what are the values of this. By using alpha, we can control this parameter. By using beta, you can control this parameter. Okay. Yeah, by alpha, you can control this parameter and by beta, you can control this parameter. So this is the expression which gives the probability of selecting any path. Okay. So if the value of this expression is more, then more probability will be there. Okay. This expression for calculating the probability of selecting any path. I'll show you how to calculate this one. Okay, by this expression, if I'm taking the first path, okay, see there's one numerator and 3 paths are there, so summation of 3. So the value you will get here is 0.79595. That is the calculation with respect to the previous formula. We are using the previous formula and we are calculating it like this. We are using this formula and we are calculating this. So if you are calculating for these 3, if for the first path you will get, because all values are there, 0.7595. The second path you will get 0.50 something and third path you will get 0.1899. So that will give you the probability of these 3 paths. You can see here. So probability of selecting the first path is 76%. Probability of selecting this path is 5%. The probability of selecting the third path you will get as 90%. Okay, that is the condition. You can see here. You can see here the pheromone content here is 0.6. The pheromone content here is 0.57. The pheromone content here is 0.53. Obviously, it is understood that this path have more probability. This path has a next probability, and this path has the highest probability. Or if we see this path, it's 0.1, which has more probability because pheromone content is more. 0.03, it's very less. 0.07 is in between these two. So it can select this path, which is have more probability, or it can select this path. This has a least probability, depending upon the pheromone content. Same, your calculation will give. This path is having 76. So this, depending upon this expression only, the ant will take the next path. So this is done after one iteration. In the second iteration, so most of the ants will take this path. 76. Okay. Now we'll see one more example in this one. Okay. See, I have seen all these things with 1, 1, 1 only, because initially it was 1, 1, 1 for everything. But we'll take one more example. If this is 5, if this is distance is 1, pheromone is 1. Here the distance is 4. Now I am changing the pheromone from 1 to 5. So if this is 5, what will happen? Okay, with the same calculation, if I am putting 5, this path is having 43, this path is having only 2%, and this path is having 53%. So now the probability has changed. Initially, the first path has got more probability, but now the pheromone content here, just I changed it. So now the probability is changed. You can see here. Yeah, you can see the two cases. So first, now this is 54% you have, because the pheromone content is increased to 5. Okay, since the place pheromone content is only 1, the probability is just 43. So from this we can understand that both pheromone content as well as the distance will decide all these paths and all. So this is how you need to code and colony optimization. First write expression for pheromone, then write expression for total pheromone, then we can write expression for the evaporation factor, and finally write the expression for your probability. When you can write all these for the entire ratio. Okay, now we can see the probability it is changed. Okay, and now, and this probability normally you will be using Rowlett-Weil method to give the conditions, because we can't tell the ant to go here and there. They need to put some conditions. If this condition is satisfied, take this path. If this condition is satisfied, take another path. For that, we need to normally we will go for Rowlett-Weil method. You can see the first path has 76%, the second path has 19%, and the third path has 5%. So how Rowlett-Weil is working means 0.76 plus 0.919 plus 0.05, this is 1. This 0.19 plus 0.05 is 0.24. It's only 0.05, this is here. Okay, so this is a cumulative sum. Okay, so depending upon this sum only, we will generate some random number and we will tell them to take the path. This will be like this. Okay, I'll generate one random number between 0 and 1. So after calculating the probability, I'll calculate a random number between 0 and 1. Okay. If the number is between 24 and 1.2, because you are generating between 0 and 1. If the number is between 0.24 and 1, go to the first path. That is this. If the number is between 0.05 and 0.24, these values, take the second path. Because see, your program can't understand which path it has to take. We need to give some conditions. Depending upon the conditions only, it will take. So we'll generate a random number between 0 and 1. If the random number generated is between 0.24 and 1, surely it will take the first path. If the random number generated is between 0.05 and 0.24, that is this value, it will take the second path. And if it is between 0 and 0.05, it will take the third. That is how the path it is taking in the second time. And you can understand that when you are generating, it's from 0.24 to 1. So 76% probability is there for getting such a number, right? 76% probability is there for getting such a number. That's how the probability we have is 76. So this is how we'll be using Rowlett-Weil method to find the path. Okay. And these are the steps for ant colony optimization. And see, you have nearly 3 or 4 parameters in ant colony. One is alpha, one is beta, one is Q. 3 or 4 parameters are there. I'll tell how. So I'll just take a glance how to select these parameters. We have alpha. In this expression you have seen, we have beta, we have evaporation factor rho, and pheromone strength. But this one, most of the cases they may use or they may not use. But 3 things are there. Alpha is there, beta is there, and rho is there. Alpha and beta you can see in the probability equation, and rho you can see when you are calculating the evaporation. They will give the range from 0 to 1. But how to use these values? What is the range of alpha and beta? That I'll just tell you. Okay. See, when I'm taking alpha, okay, if alpha is very high, it indicates that more pheromone is there. Okay, if alpha is if I'm taking alpha can range from 0 to 1 or any value. If I'm taking very high alpha value, then your tau value will be very, very higher. Tau value is high means it indicates that more pheromone content is there in that path. then what will happen is that more ants will try to flow through that path. So what will happen means that convergence speed will increase because only one path is having highest value, convergence speed will increase. But very less chance that you will get a better answer because you have increased alpha. So only one path, everything is flowing. So the remaining other path, they won't flow. So within one path, you will try to find the optimal value that you won't get the exact answer. So if you're taking highest value of alpha, your convergence speed will be very high because only one path it will be. Okay, but there's very less chance to get a good answer. Okay, yeah, but it can result in local optimum. Whereas if I'm taking less value of alpha, the pheromone content will, because tau power alpha, if alpha is very less, then tau value will be very less. It indicates that the pheromone content in that path is very, very less. So the chance of using that path will be less. It will flow through other path. So what will happen is that your convergence will be very slower. But since it is using lot of other paths, okay, there is a chance that you will get a better answer. So the first case, convergence will be faster, but less chance of optimal result. The second case, convergence will be very slow, but there is a chance that you will get an optimal answer. So your value should be within maximum and minimum lengths. Okay, convergence speed will decrease. Okay, because a lot of path it will travel. But global search, it will search for all the paths so that you will get a better answer. Okay. A normal range of alpha is between 0.7 and 0.9. In most of the problems you can see, they'll take alpha as 0.7 and 0.9. And if I'm taking beta, okay, if I'm taking beta, if beta is 0, only tau will be there at the pitch. Okay. If both are large, what will happen is that if alpha and beta both are large, your program will come to end prematurely. You won't get the actual one. Okay. But whereas if both are very small, it will take lot of time to run. It will never converge. So beta range you need to take beta range you need to take between 1 and 1.5. Normally, if you see problems, you will get like this only. If you are taking alpha and beta higher means certainly it will converge, but your answer won't be perfect. If alpha and beta are very less, it will converge. It slowly. It will take more time. So the thing is that beta normally people will take from 1 to 1.5. Alpha is from 0.7 to 0.9. And next parameter is evaporation factor, rho. Okay. So the evaporation, this rho will tell you how much evaporation is there. So if I'm taking rho as 1, it indicates that it's actually as per the expression, it is 1 minus rho. If I'm taking rho as 1, it will indicate it's 1 minus 1, it is 0. So entire thing has got evaporated. Okay. If I'm taking rho as 0, so the entire pheromone content will be there. So two options are there. If I take 1, everything will go off, everything will evaporate. If I'm taking 0, everything will exist. Both are issue. Either you can't take 1 or 0. If you take 0, the problem will be there. Okay. If you take 1 also, you have problem. So it will be between 1 and 0. Because if I'm taking very less value, it indicates that nothing has been evaporated. Okay. So there is no option to search the other path. If I'm taking very large, it indicates that everything has evaporated. So then it will go here and there, search all the path. So it will be very slow. Okay. So don't take high value and don't take very low value. The value of rho should be within that range. Okay. So pheromone strength Q normally in certain applications will be LV. Okay. So hello. Hello, sir.
Hello, sir.
Yeah. Is it time still there or?
You can continue for next 5 minutes, sir. No issue.
Okay. I'll just tell you how to apply this in economic load test match.
Okay.
Just a I'll tell you. Okay. Because within 1 hour it won't be sufficient to do all these things. I'll just tell you. I think most of you know what is economic load dispatch, what we are going to do in economic load dispatch and all, right? So as far as economic load dispatch is that concerned, we'll be dispatching the generators such that the cost is minimum. Sometimes we'll go for the loss also minimum. Okay. So that is a normal condition, right? Dispatch means the generation level is what we need to optimize such that all loads will be served at minimum cost. Okay. So the objective of economic dispatch is to minimize the overall cost of generation. That is a general thing about economic dispatch. But you have a lot of conditions, lot of constraints also. Okay, I'll just tell you. This is a economic load dispatch problem. I need to minimize the cost. Okay, And most of from power system, you can understand what is A, B, C, the other coefficients. P is the power. Okay, only variable you have is the power. And there are a lot of constraints. That means whatever power you are generating, this total power should be equal to the load plus the demand. So that is one constraint. Okay. And there are a lot of other constraints are also there because generation, each and every generator has a minimum and maximum limit. Okay. So your power has to be between minimum and maximum limit. Reactive power also has to be maximum and minimum limit. So I'll just tell you, this is a flow chart. This I took it from lambda iterations. If you forget the lambda iteration, this is a generalized flow chart which we use it for economic load dispatch. Okay, I'll tell you where to incorporate and how to incorporate and colony optimization inside this. Okay, see, this is actually the flow chart which is there for economic load dispatch, and you will never change anything inside. If you have a code of economic load dispatch, you don't want to change anything inside, let the economic dispatch algorithm be there. I'll just tell you where to change it. This is the starting of this is actually an colony optimization. So if I'm taking, for example, I'm taking IEEE 30 bus system. I have 6 generators. If I think so, 6 or 5 generators are there. So initialization of parameters means you need to each and every generator has a minimum and maximum limit. So you need to generate the values between maximum and value limit. So the difference you need to understand when you go for analytical methods, we won't feed any maximum any value inside. Finally, you will get the solution. Whereas when you go for optimization technique, initially we will generate solutions and we will test it. So in this initialization, what we need to do is that we need to generate, for example, if I am having one generator with a minimum limit of 10 and maximum limit of 60 means generate a solution between 10 and 60. So 5 generators means 5 solutions minimum you need to generate. That's the difference. Okay. Then the same ant colony you can use it only when you're going for calculating fitness function. You put your economic load dispatch coding inside this one because calculating fitness function means that economic load dispatch problem only. Okay. But only thing is that the initial solutions will be taken from the optimization problem instead of feeding the power from that generation matrix, because when you're going for load flow, economic load dispatch, you'll be having 2 matrices, right? One will be for line data, other one will be for bus data. So in the bus data, you'll have power generation and all. So those, instead of feeding those data, you take the power generated by this initial solution and use it for your economic load dispatch. Okay. And whatever output you are getting from this one will go to the next step, because after running economic load dispatch, you will get the power generated, right? P1 to P5, you will get the answer. Again, you continue this. Then again, this will continue. This loop will go here. Again, it will run like that's all. So only thing what you need to do is that initialization of parameters, just do depending upon the number of generators you have. Then the place where fitness function is coming, incorporate your economic load dispatch problem inside and run it. That's the only difference you can make. You need to do inside, because the thing is that these are meta heuristic systems. Their algorithms, the algorithm is fixed. It will never change with respect to your problem. Okay. Only thing is that initial parameters depends upon your system. If it is economic load dispatch means you need to go for generation. If you are going with fax device means the variables of fax device. If you are going for unit commitment means the status of the units. Like this, things will come in the parameters. And while calculating fitness only, take the values which are generated from the initial parameters and run your economic load dispatch. And after running economic load dispatch, you will get an answer. That answer you use it here. Then you run ant colony. This is actually the process of running ant colony optimization. Okay. And one more thing I can tell you is this. Okay. Because all steps are given, but I can take all these things because we're already running out of time. The thing is that, see, this is a fixed algorithm, but there are a lot of algorithms, we'll call it as hybrid algorithms too. Because there are some algorithms which have a lot of advantages, there are some algorithms which have few problems are there. Okay, in algorithm, we can't tell all algorithms are perfect, or we can tell that all algorithms are worst. Some algorithm, they are perfect for certain applications. So all algorithms have its own advantage and disadvantage. So what they will do is that they will take the very good properties of some algorithm, 2 algorithms, and they'll mix together. Then they will make it as a hybrid algorithm. That option is also there. Okay. So just one, I'll tell one more example. If I'm taking, see, since it is power system, I'll tell one example with the power system. If you're going for power system, you have one problem which we'll call it as unit commitment problem. When you're going for unit commitment problem, first one you need to do unit commitment, then you need to go for economic load dispatch. But when you go for unit commitment, the answer is only either the unit is off or on. That's all. So off means you'll put us one, and on, sorry, off means you'll put us 0, and on means you'll put us 1. So 1 or 0 only, the answer you will get it from unit commitment. For such things, you can use binary coded algorithms. Okay, but when it comes to economic load dispatch, the binary 1 and 0s won't work. I need to have power generation values. So there you can go for real coded algorithm. So from the same problem itself, you can use these different techniques. Unit commitment, we can, for example, if I'm taking ABC algorithm, while solving unit commitment, I can use with binary coded ABC. While solving load dispatch, economic load dispatch, I can now use with real coded ABC. So that in the same problem, you can use two algorithms and it. So it doesn't mean that you can use only this one. And when you go for ABC, now you have another one, nodal and colony. You have a Turing on colony. All such applications are there. But this is the basic and colony optimization. Okay. And if you have any queries or if you have any doubt or if you need any help in this one, I just gave you a person number. You can put a message in that. Surely I will help you out. Okay, because we don't go beyond this timing. If you have any doubts or if you have any help, you need anything in this, please feel free to put a message in this one. Surely I'll help.
Okay, sir. Thank you very much. It's time. Thanks. Thanks given by Mrs. Divya. Please carry on.
Hello, sir. Am I audible
Yeah.
clearly?
Yes.
Okay, sir. Thank you very much. Good evening, Honorable Srijit Shekaran, sir. And good evening, everyone. Respected Secretary, sir, Principal, ma'am, Dr. Brahmaya, sir, HOD, sir, and all my colleagues and participants. It's my privilege to have been asked to propose a vote of thanks for this wonderful session. I'm Divya, working as Assistant Professor in EEE Department. On behalf of our St. Peter's Engineering College, I want to express my heartfelt thanks to Dr. Srijit Shekaran, sir, for his magnificent session on ant colony optimization techniques for power system application. Sir, in spite of your busy schedule, you accepted our invitation and taken striking a section. So it is given a very fruitful result to all of us. Thank you, sir. Thank you very much for your eminent session on this day. Thank you, sir. Hello.
Thank you, Divya, ma'am. It is time.
Thank you, sir.
This meeting is ends now.
Hello.
Thank you, Sejit sir, for sparing your time for us. Thank you very much.
But it's really bad to that I'm not able to answer the question since time is already over. But still, if they have any queries, feel free to put a message on my mobile. Surely I'll reply. Okay. Thank you very much, sir. Thank you for providing me this opportunity. Thank you.
Thank you, sir.
Thank you, sir. Thank you very much.